Yeah, good morning, everyone online. Today, it's our great honor to invite Professor Matthias Heinrich to give us exciting webinar. This is the first IEEE MBS webinar series this year from Frontiers of Biomedical Imaging and Analysis. And today, Professor Heinrich will introduce his recent cool works in INR for medical image retrieval modeling synthesis. First, let me briefly introduce Professor Heinrich. Professor Matthias Heinrich is full professor of medical image processing at the Institute of Medical Informatics, University of Lübeck. He received his PhD from University of Oxford, where his dissertation on deformable lung retrition was awarded BMVA Sullivan Prize for the best computer vision thesis in the UK. His research focused on machine learning methods for medical image analysis with applications in multimodal retrition, reconstruction, and ultrasound imaging. He has been recognized with several awards, including the prestigious MICCAI Young Scientist Award, the MIDL Best Paper Award. Professor Heinrich also served as a board member of MIDL Society and associate editor of IEEE Transactions on medical imaging. Okay, so let's welcome Professor Heinrich, and the stage is yours.
Thank you so much, Young Kai, for the nice introduction. Thanks everyone for tuning in and listening. So yeah, today I thought I give a presentation on implicit neural representations. Quite a new field. Maybe not all of you have heard about this in so much detail. So yeah, maybe it's something to learn for everyone here and raise your interest. So as you're all familiar with, neural networks are really good at fitting complex nonlinear functions. But to date, most neural networks have predominantly been used for learning with training data. So you have like some population with labels and you train your neural network on them. But implicit neural representations leverage them in a quite different way. They try to fit test data without the need for extensive training data, but make use of the neural network really as a nonlinear function approximator in a way. And this gives rise to a lot of new cool applications that do not require a lot of training data, but still can benefit from GPU acceleration and all the benefits that neural networks bring to machine learning. The rise of the INR has been quite steep over the last couple of years. Early coordinate MLPs have been introduced in 2019. 2020 was probably the most important year for this field. Siren, one particular architecture of INR, was introduced, and neuroradiant fields were introduced in the graphics community that somehow revolutionized 3D modeling in a way that followed up in the coming years in 2021 and 2022. And then it sort of trickled down to other fields, was used a lot in computer vision, other graphics fields, but also in medical imaging. And since last year, I think in every major computer vision, machine learning or medical imaging conference, you will see papers on using implicit neural representations or INRs. It's still not the biggest field, but I think looking at it is quite meaningful. So in my talk today, I want to first introduce the key idea, which is how we can encode an image or some other data point as a nonlinear function as an MLP. I then want to go into some basic methods. What are the limitations of a standard coordinate MLP? And what are the solutions to make it practical using a sinusoidal activation or some encoding of the coordinates, Fourier or hash grid. Then I want to move to applications. Reconstruction is the most prominent one for INRs, in which we can create a super resolved image or 3D volume of a scene based on, for example, multiple smaller, lower resolution 2D images. And we can also reconstruct shapes or represent motions. We can build implicit atlases or just use it directly for deformable registration. And we can also condition INRs and then bring a little bit back the kind of population training that we are used to from machine learning. Finally, I want to discuss a bit synthesis of new images, new shapes, and how we can use it for practical applications, in particular also privacy, and then follow up with a discussion or Q&A. So normally, if you use a neural network, you would have an image as an input and feed it into your MLP, and then you get some classification, some regression value out. INRs work fundamentally different. Here, our input is actually a grid of coordinates, X, Y coordinates that make up like the space where the image resides. And your output are gray values. So if we have a 2-channel input, X and Y, and a 1-channel output from our MLP, we can reconstruct the intensity value for each of the coordinates. And we fit the weights in our multilayer perceptron so that they match the intrinsic representation of this 2D image. So it's specific for one particular image. So it's no population training. It's just a single instance that we're looking at. And it can be either an underrepresentation, kind of like a compression of the actual data, or an overrepresentation where we have a little bit more parameters than are actually needed. It can reduce some redundancy of the images. We can remove noise directly by just kind of not fitting the noise to the data. And we could directly use it for kind of restoration tasks, such as inpainting missing areas, etc. INRs are resolution agnostic to a certain degree, which means that even if I haven't sampled the image on a particular resolution, I can still probe the trained network using a new coordinate at, for example, double the resolution or half the resolution or something like this. But to make this work, some specific activation function or some specific conversion mapping of the input is important. And this is also the reason why this hasn't been picked up earlier on. As we can see from the image here on the right-hand side, a basic coordinate MLP with ReLU activations gives really poor quality reconstructions. And in 2020, 2 different approaches have emerged that work much better and solve this issue. One is the coordinate encoding, which means that instead of directly putting the coordinates X and Y into the MLP, we first map them into a frequency space, for example, similar to a Fourier transformation. The other one is using a different activation function. So instead of ReLU, which we all know is the best, or more or less the best for neural networks, we simply replaced it using a sinusoidal function. Sine is used in the most popular version, the siren of an INR. It could also be an exponential Gaussian function or a mixture of them. And if we do this replacement, then actually our reconstructions start looking much better. So Sitzman proposed the siren, and in this seminal paper also showed some nice properties of INRs for several applications, going beyond just shape representations, but also inpainting, solving wave equations, etc. And I think from this short video from his webpage, we can see quite nicely how well a siren is able to fit the data in just very few iterations compared to the ReLU or some variants of the ReLU, and how it's not only reconstructing the image itself, but also the gradients adhere much more to the original gradients and the second order ones as well. And it's really easy to implement. So here I show some example PyTorch code where we simply change the forward pass. So in this example, the linear layers of the network are in this list called net. So I call them one after another, going through the different steps. And these are basically the 3 versions that I could use as a forward pass. I could use a ReLU, which wouldn't work great. I could use the sinusoidal activation or the exponential one, or I could also mix them, which which then again can be quite good. One thing you will notice here is that I'm not only applying the sign as an activation, but I'm also scaling my output beforehand. And this is because the periodicity of the sign function needs to kind of match the range of expected values that come out of my network for my linear layer. So as the scale is a hyperparameter that I need to fine tune. Often 30 or something like this is used, but it depends on your problem. If you have a very slow moving signal to fit, then you can use lower values. And what's also important is the input and the loss. So as I mentioned beforehand, our input now is not an image, but it's a grid of coordinates. So in PyTorch, I would use functional affine grid with an identity transformation and shape it as a tensor with 2 channels and feed this into the model. And it returns, in this case, just a vector that I can reshape to look like the image. And my loss function is actually comparing the output of this INR with my input image. And then I backpropagate the loss, optimize over the model parameters, and then I will fit the INR. The initialization is also important because we have this different activation function. It's important to slightly adapt the way we initialize weights to fit more quickly. And if you want to play around with this, we created a small tutorial for a local conference this year that you can find in this following GitHub code, link. To visualize this, I took a simple CT slice and fit the ReLU MLP, the siren, and then a combination of both. So in this case, the siren, the sign activation is used for the first and last layer and the ReLU in between. And in the different rows, we can see like an increase in the number of channels in the MLP. So we have 80. We still have fewer parameters than pixel in the image, but I think the reconstructions are already pretty close to the ground truth for both the siren and the siren plus ReLU. But for the ReLU MLP, it just doesn't work. For smaller values, we have some compression artifacts, but still most of the structures are recognizable. I mentioned there's 2 ways of doing this input or dealing with the spectral bias of the ReLU. One is using different activations. One is just mapping the input. And for the input mapping, we can use Fourier features, which were proposed also in 2020. And here, this gamma function that is kind of interleaved between the coordinates and the MLP does exactly this. So we have a mapping from our XY coordinates, or a vector of the XY coordinates called V, using some kind of a basis function. And the bases are sampled from a normal distribution of frequencies. And we usually sample 32 to 64 of these basis pairs. So now we don't have a 2-channel input, but a 64 or 128 input. And then we can use any normal MLP with ReLU activations. And from these images, we can see that this works. The basic coordinate MLP doesn't work at all. If we do some more effort, we might get closer, but the Fourier feature mapping is just much more clear. The fur of the fox and the hair are much more detailed and better visible. But there's another strategy of doing it even more efficiently, which is slightly more complicated, but I'll try to explain it in a good way. This was introduced 2 years later, Instant Neurographics, which uses a multi-resolution hash encoding. So again, we want to map the input coordinates to some embedding that is useful for the MLP to learn the data from. But we want to do it for very high dimensional data, either very big images, gigapixel images, or 3-dimensional data, where the Fourier encoding would be struggling. The main idea of hash encoding is that we can represent the coordinates using multiple scales of coarse to fine grids. And we map each coordinate point to the closest grid cells. The entry for each of these grid cells is a trainable parameter, kind of an embedding, a feature that is attached to this particular grid cell in our coordinate space. And as I said, we have multiple of these levels. So we have one very coarse one, a couple of finer ones with resolution jumps of, say, 1.2 or so. This creates additional parameters to learn. So the entries to these features that are stored in the lookup table in our hash table are trainable parameters as well. And they are shared across multiple coordinates, so to speak. If my point of interest falls into several grid cells, then multiple coordinates share the same hash table entry. Because we want to limit the number of parameters, the length of the hash table is limited, so we might end up with a small number of hash collisions, which isn't a problem because we have like multiple scales, so we can kind of recapture this. To make use of like more precise spatial information, we do a bilinear interpolation of the 4 neighboring points in 2D or 8 neighboring points in 3D, just as you would for an image resampling task. From these different levels, say 8 levels, I concatenate all the embeddings that I looked up and then feed it to the MIP, and then everything else works as before. Just this initial step is slightly more complicated. It turns out this is really helpful, not just for representing the data, but also for speeding up the convergence of the MLP. Because there are so many shared informations from these multiple scales, and I'm looking at the problem kind of in a cost-to-fine optimization, it more quickly finds the correct parameters for the MLP, and therefore can fit even to very large images, 3D-dimensional images very, very quickly. Here we can see another small animation, how fast the Fourier features fit the Fox image and how fast the hash encoding fits it. And on the last image, we already see visually that the hash encoding is slightly better. As I mentioned, we now have parameters in the network and parameters in the hash table. And if we have a look at the PSNR, the quality of the reconstruction, the hash grid, just quickly gets much higher values. And this has been used in 3D graphics a lot, but also in 3D medical imaging. Here are some direct comparisons. And from the paper, they also can show the fitting time goes down by tenfold, more or less, based on the compared to the frequency encoding. The PSNR is higher than for a comparable dense grid representation, multi-resolution representation. So yeah, this is kind of a good compromise. Okay, with all these basics covered, let's move into the applications. And the first application is usually to reconstruct some information from given images. Where it's really good is if we have multiple 2D images, at least for medical imaging, this is quite a useful use case. And we want to fit a 3D volume to these multiple 2D slices that are acquired from a volume. And oftentimes we might have in medical imaging intra-slice motion. For example, having fetal brain scans in MRI and the baby moving. So if we have access to a transformation that can transform our grid rigidly to the correct slice based on some motion tracking, we could kind of reconstruct the 3D volume, giving this this coordinate information, and fit one shared implicit neural network for all the slices in one 3D stack. In this kind of most popular work, the NES4 paper, we have some additional branches that take care of things like bias field in MRI, and try to reject outliers. I'll do this in a second. But in principle, we have an MLP, hash grid encoding for the 3D coordinates, and we can fit the implicit 3D volume based on the 2D images. And here's how the results would look like. If I have an input of kind of quite severely corrupted stack of motion corrupted stack of MRI acquisitions, the NES4 implicit reconstruction is giving us a very clear 3D volume. It needs the transformation. I mentioned this, so we have to have a slice to volume registration beforehand, but we can fine tune this once there is a first good reconstruction. And as I mentioned, it's resolution agnostic. So regardless of our slice resolution or in-plane resolution, we can create any output resolution that we want. What's important here is the outlier rejection. If there are some slices that are misregistered, there's a way in this approach to downweigh them in the reconstruction so that it doesn't affect it too much, and then maybe later on we can fix the orientation and include them again. And their comparisons show that they're much better than the conventional reconstruction methods, and also much easier to accelerate because we can use standard optimizers that are GPU accelerated and neural network functions on the GPU. A similar work that has been kind of proposed a little bit earlier as an archive paper does the same idea or performs the same concept on ultrasound images. And ultrasound images are also quite often hard to reconstruct to meaningful 3D volume because we have manual sweeps. So the stacking of the individual ultrasounds needs some kind of correction, and there's speckle noise, etc. That makes like a shared representation in 3D space difficult to represent the intensities. So implicit vol takes a similar approach as NES4. It's using transformations based on some other model that estimates the motion or the pose of the ultrasound probe. It creates one 3D INR that represents the whole volume and fits all the individual frames from the ultrasound sweep. It does some intensity correction, and then you can render any 3D volume, but you can also render new views. You can obviously say, if I have a different pose that I need for this particular fetal ultrasound scan to do my analysis for some measurement, I can just create it because I can just put a new grid into the neural network as input, and I get a new simulate or synthesized 2D frame. And to show you that this is really easy to implement on your own and play around with, I created two toy examples. One is showing kind of like a simulated sequence of kind of moving a camera around on a fake 2D slice with some text written on it. So you can see like how well it is able to combine this information from the sequence of low resolution into one shared high resolution image. And the same for having a 3D stack of or 3D volume of a CT, sampling individual low resolution acquisitions with slightly different orientations and angles, and fitting a shared MLP INR to it. You can quickly see that it creates a good super resolved 3D image out of them. And moving slightly different direction, we can also use this for image acquisition models that are more complicated. CT obviously doesn't directly it uses projection images, so it doesn't directly just sample intensities at locations, but it can also be formulated in a way that we can use an INR to do reconstruction from limited view, for example, COM-beam CTs. In this neural attention field approach, we fit the MLP, the INR, to model the attenuation coefficients, and then render the different projection scans and use them as supervision during our training once we have this, we can just have a forward model to produce a CT scan from the attenuation coefficients. And here again, the hash encoding works really well because it covers these different types of frequencies, smoothness, and edges in the image quite well. And this is actually quite related to neuroradiant fields. In a normal 3D scene in the world, if you have access to a camera and have multiple images from a camera, but also the positions of where they were taken, you can create a 3D representation using an INR that not only models the intensities, the colors that you can see, but also the density of the different objects in the world, the transparency of different things. And if you've created such a 3D model, you can use it for synthesizing new views, estimating depth from the image without having a depth sensor beforehand. But yeah, as I mentioned, also really well model transparency, as you can see in this Christmas bell. It's a big improvement, I would say, over previous approaches that use CNNs to model 3D scenes from given 2D images, and is much more natural to implement, I would say. Here, the INR stores the volumetric scene, so it's 3D, and it has some view dependency. So if you're in the real world and you have a kind of a 3D coordinate, the color of the object may depend on your view direction. So a single point might have different colors, different shadings, etc., depending on the direction of where the camera looks at it. So we increase our input space to 5D, 3D location plus 2 angles. And our output should now also include some volumetric density and a view-dependent color. And here, the number of images can be quite large, so we can kind of move around the camera in a 3D scene, capture the pose of the camera using some tracking approach, and then reconstruct the whole 3D scene in a single INR. What we need to do now to define a good loss for reconstructing the 3D scene is to actually render the images based on our modeled scene. So we're basically doing ray tracing, where we go through our initial state of our INR, sample along the ray, whether there's a dense pixel or whether it's empty, whether it has some color, and integrate over that. And this volume rendering loss creates for each potential camera position a estimated pixel value in color that can be compared to the ground truth camera pixel. And we can do this of all the images in our training, in our training set. This is obviously quite computationally heavy. So using a clever strategy of doing the ray tracing and of focusing on high density areas rather than just emptiness is helpful. And we can find good ways of doing like a kind of bundle adjustment of this, kind of putting together a couple of images in each batch that are meaningful together. And again, if we use hash grid encoding, the fitting of the 3D scene is much quicker. So instead of using a couple of hours to days, it can be done in maybe half an hour or so for a 3D scene. And again, once I have this kind of 3D scene represented in an INR, I can create new views. I can estimate depth, density, etc. From it. Here, just some visualizations, how much more accurate it reconstructs some certain scenes compared to neural volumes. And the maybe tricky bit that is newer works tries to improve on is really how to best optimize the derivatives for the hash grid. So there can be some instabilities. So this CVPR paper, neural Angelo tried to replace the analytic gradients that we would normally have. So these are actually the grid cells and the hash grid. I have my location. And normally if I backpropagate the loss with respect to the embedding vectors that I try to learn, would use like the analytical gradients of this bilinear interpolation for deriving the gradients. Neural Angelo replaces this using finite differences. So we sample more points. So we have an epsilon where we offset our locations and then kind of do more interpolation. We find the finite differences and use this to define the loss. And this is actually much more stable for the gradient and still further improves the fitting. What they also do is kind of not optimizing the cost to find levels all in parallel, but they start from putting more emphasis on the lower resolution coset grids in the beginning, encode those features first, and then while optimization progresses, they add the finer and finer grids. So if you look at the reconstruction, it kind of starts with the rough shapes and then gets more and more clear on the details in the later stages. So if you work in medical imaging, maybe kind of using some of these ideas for 3D reconstruction there would also be useful. Now that we know that we can represent images, we can represent volumes in 3D scenes, how can we represent some other interesting properties of data? And one that's actually quite straightforward to do is motion. In medical image registration, there's still a lot of really good algorithms that do not use any learning anyway. So optimization-driven registration still performs best in many cases. But here we could also leverage this idea of using an INR to fit on the displacement data. So Watering was one of the first to use this for lung registration. Here the INR represents the displacement field. So given any coordinate, we can get the displacement vector. Because we have sinusoidal activations, this gives us some implicit smoothness. Because the neural network fits better than directly fitting the displacement vectors, we get faster convergence and often higher accuracy for the registration. And since we are not bound to a certain grid or a certain resolution, we can also extend this to point cloud registration. So in this example, we again see two lungs that are represented as two point clouds, and we're trying to register them. And based on this ICCV paper from 2 years ago, I tried to implement Siren on top of the point cloud registration. And from my results on the quite challenging CPD data set, I could see that the Siren really improves the optimization. I don't need an affine initialization anymore. The hyperparameter setting is much simpler than when using a B-spline transformation. Don't need to tune it that much. And I can see even lower TRE, target registration error. And it's still fast. It still just takes a bit more than a second. If I can represent motion, then obviously I can also represent shapes. And this was actually, so I'm going a bit back in history, the first use of implicit representations in computer vision. So Deep SDF, a CVPR paper from 2019, represents a point cloud using just the information of whether the point is inside or outside the 3D shape to fit an implicit surface time difference function. And once I have fitted this function, I can sample it densely. I can create a 3D volume from it using marching cubes, and have a really nice way of representing 3D shapes in a continuous space. And in the same year, kind of different concurrent approach called IMNet, combined this also with an encoding of the shapes. So beforehand, I was often said like our only input to the INR is a coordinate. But obviously we can also add additional features, additional latent vectors to this individual point, which represents like some global information. Here, the feature vector of the latent of the shape was produced using a point net, and it was concatenated to the coordinates and then fed into the MIP. And if I later on, for example, do shape interpolation over the latent space, I see this is a lot more meaningful than when I use a CNN-based autoencoder. And this latent code actually gives us a way of conditioning our INR and make it more generalizable. So if we think about fitting an INR to multiple images or multiple shapes, I would normally automatically end up just estimating the mean of our data, because there is no way of differentiating between two different data points or instances. But if I allow the INR to take an additional vector that represents each instance as an input to modulate my parameters, so either concatenate it to the input or better also use it to shift and scale the linear layers in the INR MIP, I can have shared information, the green, blue layers and parameters, together with instance-specific parameters that are based on my single data point. And with this, I can kind of do some machine learning again inside of INRs. But I still have the benefit of being able to quickly fit on test data, and yeah, kind of still using the reconstruction loss to find something on a specific data point. One example to use this is shown in this Sina paper from last year's MICCAI, Conditional Implicit Neural Atlas. Again, we're looking at fetal brains. And in this time, we are training this conditional INR that takes multiple images as input and shares the parameters of the linear layers and modulates them using some latent specific, like patient specific code that shifts and scales the output. It also has two different heads, so kind of output layers. One that gives us the intensity reconstruction and the other some tissue probabilities, so basically a segmentation. What I can do with this now is that if I've trained this for a population, have a new unseen image for which I do not know the tissue probability, I can freeze the shared parameters across the population and simply fit a new latent code to the unseen image based on the reconstruction loss of the intensity image alone. And I will automatically get some tissue probabilities for this unseen image. I did this to verify on open public dataset, the JSRT dataset. As you can see here is a ground truth image. The fit of my frozen INR to this image is kind of a little bit more blurry, but basically shows the same anatomy. And then the automatically created segmentation. The DASCO is pretty good for lungs and heart, a little bit worse for the clavicles. But it shows that in principle we can generalize kind of the INR, even though we only have this very small vector that can modulate the INR weights. What we can also do with this is we can derive some other clinical parameters. So we could create or synthesize from this atlas an image that is a representative of a certain gestational age by giving the months here as an additional input. Or backpropagate kind of what this gestational age would likely be for a given image if I just use the reconstruction loss. So there's a lot of flexibility in there if you introduce this conditioning. And yeah, I think there's still more to find out. What we also did in terms of atlas building is to disentangle the image intensities and the shapes of the different subjects. And using an INR is surprisingly simple to do this, to get much sharper and clearer atlases than the normal group-wise registration approaches that you could use with simple elastics or voxel morph. We've done this on your ACEs and the JSRT dataset, and now all the INR parameters for the atlas image are shared. And each training sample has its own B-spline transformation that warps this intensity atlas to each instance of the scans. And because, again, we have this kind of resolution agnostic representation, the resampling is also quite simple. We just have a different grid. Finally, I also did some work on how we can fit multiple images from different patients in the same INR to somehow obfuscate the individual. I don't know if you're aware of this, but in recent years, privacy preserving has become a lot more pressing issue when sharing medical data, because it became obvious that it's quite easy to re-identify a single person based on their X-ray image in a large database using a re-identification network. So to kind of combat this and mitigate these problems when sharing data, one could think of synthesizing similarly looking images that are harder to re-identify. And the idea here is to take a bunch of images, say 64 patients, use their X-rays, and fit a shared population INR. In this case, it's called a NERF. We can discuss details if you're interested later. And only have a single vector that represents each of the patients. If I directly feed these vectors into the INR, I will get pretty close reconstruction, high PSNR. But I could obfuscate this by changing this matrix multiplication, which initially was just an identity matrix, to one that mixes some of the other patients into this one patient. So the latent codes are somehow intermixed a little bit by adding this noise to the off diagonals. And as we can see from the obfuscated example, it doesn't look very different. So for example, for a segmentation task, there's still a lot of utility in this. And we verified that the dice score of segmenting the catheters in these images is still roughly about 80%. But the probability of re-identifying a person drastically reduces by this obfuscation. So we can kind of preserve a little bit more of anonymity for the patients for which the data is shared. And yeah, in a similar way, we can also kind of modulate the shape of different patients in a data set. This is a paper from this year's MICCAI, again from the Voltering group. And here they simply encode the whole data set in an MLP for different shapes of the thyroid. And they enable the latent code to modulate different aspects of the thyroid. So the volume of it, the isthmus area, the symmetry. And for each individual patient, we can now kind of create a synthetic version that fits these other meta parameters, by simply moving the latent code around a little bit. So I think this is also quite cool and gives hopefully rise to more interesting applications. With this, I'd like to conclude, a little bit sum up what I discussed. I hope now you also feel that INRs are very good at implicitly representing images or volumes as continuous functions. We have this resolution agnosticity, which is quite helpful for many tasks such as super resolution or combining multiple images to one with higher quality. We need to take care of the activation or the input encoding. So using hash grid or frequency encoding is helpful for fitting the signals better. And INRs are quite versatile. We cannot only use them for reconstruction, but we can also use them for regression tasks, shape interpolation, registration, compression, etc. And the implementation is quite simple and efficient. Um, I think like other tasks that have previously been done in quite complicated kind of group price registration is difficult to implement otherwise, or some reconstruction algorithms are really quite a lot of code that you need to work through, whereas an INRs is quite a clean and elegant implementation for these things. The population training is a little bit further behind, I would say, is not as advanced as machine learning and general image analysis for CNNs or transformers. But I think there's still a lot of scope to improve this. And yeah, if you're interested in working on this, let me know. We have a postdoc position available, so some advertisement. You can have a look at the URL there, or just email me. And with this, I'm happy to close my presentation and discuss any of your questions if there are any.
All right. Yeah, thanks so much for the great talk, Professor Heinrich. And now we have like 14 minutes for QA. And for the audience, if you have any questions, you can put your question in the QA. And Camila will read the questions on behalf of the audience. And I already see actually one question. Camila, do you want to ask the question?
Yeah, so thank you, first of all, so much, Matthias, for that amazing talk. I think this is a super exciting topic. I remember there was recently in MICCAI a tutorial on implicit neural representations, and it was so incredibly full. Like everybody wanted to participate. It was a great topic. So yeah, let me go ahead and read the first question, and everybody in the audience, please now feel free to post your questions in the Q&A box or just in the chat. So the first question is, do you think INRs can be used to simply denoise or improve the data? Will there be possible drawbacks or problems if we simply apply them to any vision data we have?
Yes, I think as a preprocessing step, they are good at doing this. They're removing some of the redundancy of the data, and also the part of the acquisition that is not like useful information. Yes, if you underparameterize them, if you have fewer parameters fitting than there's pixels in the image, then you should hopefully see some reduction of noise. And yes, there should be some advantage of this. I mean, it's also interesting to look at kind of how different INRs, the actual values of the parameters, differ across images. There are some newer works that try to kind of, for example, you could use diffusion model on the INR parameters to try to synthesize new shapes or new images based on their kind of implicit representations. So having you can think of this as a more compact version of the actual image, and therefore it would hopefully also reduce noise in the images. Yes.
Great. So the second question we have is, INRs can feed continuous functions, but although hash encoding can provide more accurate details and fast reconstruction, I found in my experiments that continuity is lost. Is there any answer to this question?
Yes, we also found this in some instances. One good example is, for example, if you have a grid, like always put in the same grid to the hash grid, but then rotate the grid, because now we have coordinates that haven't been seen during training. I think one simple way around this is to use more or less a hybrid model where you have the hash encoding, which gives you like this feature vector that you put into the INR, but you still put the coordinates in there so that there's a little bit more continuity. You can add a little bit of jitter to the coordinates that actually improves stability a bit. But I also think like this, what I showed on NeuroAngelo, helps. It prevents this overfitting on the coordinates that we've kind of we've seen, or the fixed coordinates that we would otherwise use. But yeah, there's always a risk. The other practical guide I would give is to maybe reduce the number of scales, so not go too much into the high resolution scales, at least not in the beginning of the training, to avoid this overfitting. But it's a good practical observation, and it could be a problem in some instances.
Sorry, how does adding jitter improve robustness by calculating the average between several images, or
in terms of like an yes, I would think so. Like in the NSWORK paper that I did mention, they had this variance term that was used to estimate how well a certain data point fits. And if you have multiple acquisitions, then hopefully the one that's not fitting will be removed, or at least like weight down. Yeah, they also had this kind of bias correction that you can later remove. So this is just done for fitting the data. But if you reconstruct the 3D volume, you would obviously not want the bias field, so you can leave it out. So yeah, I think like in that sense, INRs, if you have multiple acquisitions, will help you robustify your output. Yes.
yes. Okay, we have a third question. Thank you for the great overview. When INRs is used to represent structure shape as a continuous function, how easy is it to extract morphological measurements out of it? For instance, volume, thickness, branching factor. Are you aware of any related studies on this?
I have to say I'm not aware of any kind of the more topological information like branching. I mean, if you have the SDF, then obviously doing morphological operations should be easy enough. And there is works on like modeling surface normals as well. But I can't directly give a reference. But I'm pretty sure that there is good work on this. Yes.
Great. So those were all the questions right now in the Q&A chat. While we maybe wait a second for somebody else to ask, I also have a question. So you spoke a lot about using INRs for medical imaging applications, for instance, for preserving patient privacy. Do you think perhaps there is also an increased risk? And for instance, we can also do super resolution with them to actually be encoding more information about the patients that you then don't actually manage to obfuscate?
Good question. So, yeah, I guess maybe going from a different angle. If, for example, you currently if you acquire MRI or CT, you like the raw data that is in the scanner is a lot more than the actual image that is like given out, right? And that doesn't contain all the information used to reconstruct this image. So in that sense, if we have INR-based reconstruction methods that extract more information from the raw data, kind of some specific fingerprint, so to speak, of the patient, the risk would be increased of kind of revealing even more. But I would probably put it in more positive terms that you would, if you could do super resolution on like limited, for example, accelerated MRI, then this is obviously helpful because it's better to see smaller lesions or kind of pathologies. So yes, I think in the end it could carry some more risk, but it's it could also be more useful.
And sort of related to that, before I move on to the next question, how would you assess the risk of, for instance, generating certain artifacts in the images or hiding certain details that may be relevant for the diagnosis, which are maybe more rare?
Yes, I think this is true. Like this is a risk always. I think basically now we should compare reconstruction methods that work with deep learning with the ones that work with INRs, I would think. And there's been quite a few, I think, studies that show that depending on the way you evaluate them, also the way you train them, deep learning-based reconstruction can hide meaningful pathologies because they are focusing more on the like if they're not trained well, or if you not take care of like how to train your reconstruction network, then you could kind of miss these small details because you're looking for the norm more than the abnormal ones. But yes, this could also happen with the INR. It's not prone to this. Yeah.
Yeah, basically you to some extent have similar risks from the
Yeah.
yeah.
So we did try. Maybe I can quickly show this. We did try to combine the two in our recent work, where we kind of have this very kind of a combination for the population-based reconstruction algorithm for accelerated MRI, together with an instance-specific one optimization, because we do see like that reconstruction algorithms benefit from training on populations, this deep learning-based reconstruction, to kind of have some idea of the normal of all the anatomy that's normally there. But if you add the INR on top of the deep learning registration reconstruction, you see some additional benefit. You get slightly higher scores, and it's kind of agnostic to the where you do the deep learning reconstruction. So you could use any model for this.
Nice. Okay, there is a last question, which is, are there applications in which you believe using image representation is still better?
If they are, okay. I mean, yeah, I mentioned, for example, there are some ways of kind of creating, say, diffusion models on the parameters of INRs, but those are really difficult because, yes, if you train the INRs for two different images, there's like the parameters don't really match. There's so much nonlinearity in there. So I think, for example, segmentation is an obvious example where normal deep learning based approaches are probably always going to be best. And yeah, also for I would think for generative models, for diffusion models is also this is not yet the clear strategy how to do them better with RNRs. So yeah, I think there's a lot of things that you can still do without them.
That makes sense.
Great. Yeah, yeah. Limited by time, probably our Q&A session will be wrapped up here, and we'll have kind of 1 minute. And Camila, do you want to advertise the next one, the next webinar?
Yeah, so we will post more details about the next webinar in our social media channels, so please follow all of the accounts. But basically, we will have a webinar end of October again, and then we will have one webinar for the following months until next year at least.
Perfect. Great. Okay. Yeah. Thanks again a lot for the great presentation today for the uh, INR, and learned a lot from Professor Heinrich about all kinds of different applications that kind of opened a lot of new words for me. And let's thank the speaker again and wrap up today's webinar. Thanks everybody for attending the webinar.
Thank you.
See you next time.
Thank you,
Bye-bye.
everyone.
All right.
Bye-bye.
Thank you.